Welcome back to Chemical Kinetics. Today we are looking at reaction mechanism from the point of view of two different theories. One is called the collision theory and the other one is called the activated complex theory. Think of them both as two sides of the same coin. The collision theory refers usually to the Maxwell Boltzmann graph, which looks like this. We will talk about this in a bit. And the activated complex theory refers to this graph, which looks like this. Again, this is something we'll talk about again. So this has potential energy on its axes, and this has kinetic energy or sometimes speed as one of its axes. But really, they are both talking about the same thing. Reaction mechanism is the way with which we explain how factors like temperature and concentration can change the rate of the reaction. So, an explanation of why increasing temperature increases the rate of the reaction, or why increasing concentration increases the rate of the reaction, usually. In order to explain this, we posit this idea that the rate of a chemical reaction is directly proportional to the number of effective collisions per second. So then comes the question, what is an effective collision? So a collision is considered to be effective if it has the right amount of energy and if it involves correct orientation. Okay, so we are saying that as the number of effective collisions increases, the rate of the reaction increases. To explain what we mean by orientation, let's look at this small diagram. So we think that in order to form the product, which is the blue triangle with the pink circle, they must meet each other in the right orientation. Whereas when the collision happens in the wrong orientation, we say the collision is not effective in producing a reaction, and after this the particles just rebound unchanged, so they just stay as they were as reactants. The other condition of a collision being effective was having sufficient energy. So we think that when these two reactants collide, they must have a certain bare minimum threshold energy without which they will not make the change from reactants to products. This energy is called the activation energy. It is written as EA. So then let's use this newly learned information to go back and try to explain how factors like concentration and temperature can change the rate of the reaction. Why does an increase in concentration increase the rate? Well, we know that the rate of the reaction is directly proportional to the number of effective collisions. An effective collision means collision having minimum energy and the right orientation. Now, increasing concentration of a reactant will not change the activation energy that is required, but it does increase the total number of molecules available to collide. Hence, it increases the total number of collisions and hence also the probability that those collisions will have the right orientation. Therefore, increasing concentration will increase the rate of the reaction. Now remember that decreasing the volume of a gas is the same as increasing its concentration or increasing its pressure, so that will also increase the rate of the reaction. Now let's look at how does temperature affect the rate of a reaction. If you remember, temperature is directly proportional to kinetic energy, which is saying that if a system has a higher temperature, it has higher kinetic energy. Or if we say that some particles are moving faster, it is the same as saying that they have a higher temperature. In a given sample, not all particles have the same energy or speed. There is a distribution of energies and speeds, and the temperature only reflects the average kinetic energy or the average speed. The variation in speeds and kinetic energy can be plotted on what is called a Maxwell Boltzmann curve. Just FYI, this curve comes from this equation. You never have to use this equation in high school, so don't let it bother you. All you need to know is the graph that this equation generates. For a given sample, a given number of moles of a gas, the distribution of kinetic energy or speed looks like this. At a particular temperature, there are particles that have very low speed or kinetic energy and some that have very high kinetic energy. In theory at least, there is no limit to the maximum value of kinetic energy, and somewhere here is the most probable kinetic energy. The mean kinetic energy is somewhere to the right of this value, but we can keep things simple for now. The area under the curve is the number of molecules in this sample. On this graph, activation energy is represented as a straight line. So, all molecules under the green curve past the pink line have energy greater than activation energy. So, their collisions in the right orientation will produce products. Those that are to the left of the activation energy may collide in the right orientation, but will still not form products. Before we look at how to use the Maxwell Boltzmann curve to explain increase in reaction rate with increasing temperature, let's look at a practice question. Reactions R1 and R2 are at the same temperature, but EA1 is greater than EA2. Decide which reaction is faster and explain why. So let's draw a new vertical line representing EA. Now the question says EA1 is greater than 2. So on the kinetic energy axis, pink EA is greater than the blue EA. So let's call pink 1 and blue 2. This means that the area under the green curve to the right of the blue line is all the molecules that meet the minimum energy requirement for reaction 2, whereas only the pink area under the green curve are the molecules that meet the minimum energy requirement for reaction 1. So, reaction 2 will be faster. On the test, you can write this as reaction 2 is faster because it has a lower activation energy, which means a higher number of molecules meet the minimum energy requirement to form the products. Sorry, I haven't written down the complete answer here, but you should be able to write it better on the test. On our test or on the AP exam, you don't have to write complete paragraphs or even complete sentences, but please complete your thought using correct terminology and make the connections explicit. Having learned the basics of Maxwell-Boltzmann graphs, let's come back to the question of how these graphs help us explain why the rate of the reaction increases with increasing temperature. So what happens to a Maxwell-Boltzmann distribution of kinetic energies when we change the temperature? Let's start by drawing the usual Maxwell-Boltzmann curve at some temperature T1. Now, for some other temperature T2, if T2 is greater than T1, how do we draw the graph? Well, this tells us that kinetic energy 2 must be greater than kinetic energy 1. More molecules are moving at a faster speed. Since the total number of molecules and hence the area under the curve is not changing, the curve flattens out slightly and the top of the curve, the most probable kinetic energy, moves to the right and down. Now, for some reaction, if the activation energy is the purple line here, then at temperature T1, only the molecules in the pink area meet the threshold energy requirement, whereas a higher number of molecules in the blue area meet the energy requirement. Hence, the rate of the reaction is higher for the blue curve at the higher temperature. On a test, make sure you write a complete answer, making the connections between the fact that the higher temperature means that there is a higher number of molecules that possess the minimum threshold energy of collisions, and hence there is a higher likelihood of a collision of correct orientation to form products. Now, before going back to the other factors that affect the rate of a reaction, there is a slight deviation. But this is the only other kind of question that is asked about the Maxwell-Boltzmann curve, so let us cover it right now instead of leaving it for later. Maxwell-Boltzmann curve can be drawn with similar shapes for both kinetic energy or speed as the x-axis. At a given temperature, the Maxwell-Boltzmann curve for kinetic energy is the same for all gases because kinetic energy is directly proportional to temperature. So if we were to draw hydrogen, oxygen, carbon dioxide, the kinetic energy curves would overlap. However, this does not mean that the speed of all molecules is also equal. If we keep kinetic energy constant, such that kinetic energy of hydrogen is equal to the kinetic energy of oxygen, then using the kinetic energy formula, we would get the expression half mass of hydrogen times velocity of hydrogen squared is equal to half mass of oxygen times velocity of oxygen squared. This means as the mass decreases, to compensate for that, velocity must increase, or the other way around. If the mass increases, then to compensate, velocity must decrease. So the heavy molecules move slower and the light molecules move fast. We would show this on the Maxwell Boltzmann graph as follows. The curve to the left is oxygen and the one to the right is hydrogen. So can you draw carbon dioxide on this graph? Pause and try. On a test, you might be asked to draw curves or have a multiple choice question asking you to identify a curve as a particular gas and so on. To recap, we have now looked at explanations for why the factors of concentration and temperature change the rate of the reaction in the way they do. Let us now look at the third factor, which is the catalyst. If you remember from biology, catalysts increase the rates of reactions without themselves going under a permanent change. Enzymes are biological catalysts. We think this is because a catalyst allows the reaction to proceed by an alternate pathway or mechanism in which the activation energy is lower than that for the original reaction. Now we can show this on the Maxwell Boltzmann graph that we just learned as here. This is the Maxwell Boltzmann curve. We show the activation energy for the reaction, and then when the catalyst is added, the activation energy is lowered, so we can show the new activation energy as a new vertical line to the left of the original activation energy. And now we can say that the reaction is faster using a catalyst because a higher number of molecules possess the new lowered minimum threshold energy requirement, and hence the likelihood of a collision of correct orientation forming products increases. Good. Another way of looking at a catalyst speeding up a reaction is the activated complex theory, which is shown as a potential energy graph. The idea here is that the reactant molecules start at some initial potential energy, and as they come closer to each other, the compression increases the potential energy. It reaches a maximum where the two reactants form what is called an activated complex, the collision in the correct orientation. Another term for this is the transition state. And then this activated complex breaks up to form products. You can think of this as the products rolling off the hill to the new potential energy for this level. This distance from the reactants to the top of the potential energy hill transition state is the activation energy. In theory, all chemical reactions are reversible. For the backward reaction, the activation energy would be this new difference. In the way it is drawn here, it should be intuitive that the backward reaction would be slower since the molecules have to climb a larger hill to go back, a higher activation energy backwards. On a side note, the net energy difference between the reactants and the products is the delta H, the enthalpy difference. From thermochemistry, if you remember, if the enthalpy of the products is less than the enthalpy of the reactants, the reaction is exothermic. Heat has been released. Coming back to catalysts, we believe that a catalyst lowers the activation energy by providing an alternate pathway for the reaction to proceed, which can be understood by the hill analogy. Adding a catalyst gives a different, less taller hill for the reactants to climb to form products. This is the new lower activation energy required. More molecules can possibly cross this barrier, and hence the rate of the reaction increases. It is important to note that the catalyst decreases the activation energy for both the forward and the backward reaction by the same amount. Also, the catalyst does not change the delta H value at all. To recap, we can show the effect of a catalyst in increasing the rate of a reaction on both graphs like this. On the Maxwell Boltzmann graph, You draw two vertical lines for activation energy. On the potential energy graph, you show an alternate pathway which shows a lower activation energy when using the catalyst. While we are here, let us take a quick look at the type of questions you might be asked on the activated complex graph. So one type of question is where you're given a graph and you're asked to read different values from that graph. So for example, you're given this graph and you're asked for what is the activation energy, or what is the c-axis, what is the change in enthalpy, is this reaction exothermic or endothermic, and so on. So let's look at the graph. So you're starting at some value for the reactants. They are going up. So this is your transition state. It is also called the activated complex. And then you're falling down to form the products at this flat line here. So then activation energy is the difference in going from reactants to this transition state. So on this graph, it is just J. Because we have no actual numbers here, we cannot read the actual value of the activation energy. But it, it might seem very easy to you right now, but this is actually the kind of questions you will see even on the AP exam. Okay, so they're just looking for, do you understand where the activation energy is shown? What is the c-axis? Well, if you remember, the c-axis is potential energy and the d-axis is the reaction coordinate or reaction progress. So C is potential energy. The change in enthalpy is the difference in the energy between the reactants and the products, which on this graph is just H. Now looking at the graph, can you say, is this endothermic or exothermic? So remember, if the reactants lose energy to reach the products, that is an exothermic reaction. Whereas for an endothermic reaction, you would start here with reactants and the products would have a higher energy. So whatever else the graph did, the products would end up being higher than reactants and then it would be endothermic. Okay. So reading seems fairly simple. The other kind of question that you might get, and let's look at an example of that, is where you're asked to draw the graph. Now, when they ask you to draw something, they will have to give you the activation energies and the change in enthalpy. So in this case, that is given to us partially on the graph itself. So they've told us that the reactants, maybe I should read the question for a second. So draw a fully labeled potential energy diagram for the exothermic reaction whose equation is given to me. So in chemistry, the way we write something, so whatever is on the left is the reactants, whatever is on the right is the products. This is a relative description. You could write the reaction backwards and then, the name, these would become the new reactants and these would become the products in the case of a backward reaction. Anyways, so they've given us that the reactants start at this potential energy 0 and then the activated complex or the transition state is formed at some energy above that, plus 32, and there are no units here, so maybe I'll introduce kilojoules as the units. And then the products reach at negative 54. So this is all you have to do is complete this curve falling down to products. And now, given this information, we are just trying to figure out what is the activation energy. Well, they've already given it to us. It is 32 kilojoules. What is the delta H? So we find the difference between products and reactants. So H products minus H reactants. So that is delta H, which is negative 54 minus 0. So my delta H is negative 54 kilojoules. The negative is saying that this is the amount of energy released. So this is an exothermic reaction, which they had already told me. Simple enough. Now the next part of the question says, what is the activation energy for the backward reaction? So as I was just saying, backward reaction is just a relative way of writing the reaction in the opposite direction. So if these products were going up to form the same transition state and then breaking down to give the reactants back, what would be the activation energy for that? So again, you just simply read it from the graph. What is this distance? Let me make space for myself. So this distance is this 54 plus 32, which is 86 kilojoules is the activation energy for the backward reaction. And then what is the delta H backward? Well, again, so now you're starting at some value and you're ending at some value higher than that. So this is a positive value plus 54 kilojoules. That is the change in enthalpy going from here to here. So this is delta H backwards, and now energy is absorbed. So this becomes an endothermic reaction in the backward direction. Then comes the question, which reaction is likely to be faster and why? When the activation energy is lower, it implies a faster reaction. That is because the minimum energy requirement for an effective collision is lower, which means more molecules might possess this minimum requirement and hence more likely to have more effective collisions, hence a faster rate. So in this case, which is the one that has the lower energy requirement? Well, that is the forward reaction. So we expect the forward reaction to be the faster reaction.